morning, good afternoon, good evening, whatever the case may be. We are back and better than ever. And this is part 2 of the Cayley table. So let's get right to it, shall we? Construct a Cayley table for the addition modulo 5. That just means mod 5 on S equal to 0, 1, 2, 3, 4. Okay, so let's do it. 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. I'm going to put plus, and then I'm going to put a little 5 in here to remind me it's mod 5. Now, remember, mod 5 actually, a little bit of a coincidence here, but for mod 5, our only answers can be 0, 1, 2, 3, or 4, no matter the operation. And the operation we're testing is addition. So, 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 2 is 2, 3, and 4. So it's just addition. 1, 2, 3, 4. Ooh, here's 5, but we're in mod 5, okay? So 5 divides 5 with a remainder of 0, okay? So we have 2, 3, 4, 5, which we just found was 0. And 2 plus 4 is 6, but mod 5, that gives me a remainder of 1. 5 divides 6 with a remainder of 1. So 3, 4, and you can kind of see a pattern here. 3 plus 2 is 5, but mod 5, that's 0. 3 mod 3, 3 and 3 is 6, but mod 5, that is 1. 3 and 4 is 7. 5 divides 7 with 2 left over. And then finally we have 4, and you can see how this is working out. In mod 5, 4 plus 1 is 0, or the number 5. 4 plus 2 is 6, mod 5, that is 1. 4 plus 3 is 7, mod 5, it's 2. And 4 plus 4 is 8, so mod 5, that is 3. All right, so let's start answering our questions. Okay, so A, is the operation closed on S? Is everything in here, every answer in here, an element of our original set S? And the answer is yes, so it is closed. B, is it commutative? Okay, well, let's take a look at our main diagonal on the Cayley table. So we'll go pink again here. That's going to be, let's see, this one from top right to bottom left. I think last time I included the operators. I apologize for that. So we have symmetry. We got a 0, or we have 1, 1, 2, 2, 2, 2, 3, 3, 3, 3, 3, 4, 4, 4, 4, 4, 0, 0, 0, 0, 1, 1, 1, 1, 1, 2, 2, and then we have a 3 here. So is it commutative? The answer is yes. And remember what commutative, oh my gosh, I did that with lines. What commutative means is does A star B equal B star A? So let's just do a couple of quick checks. 2, well, let's do it. Let's see, 1 and 4 is 0, and 4 and 1 is 0. Okay. 4 and 4 is 3, and then 4 and 4 is 3. 0 and 0 is 0. And then if you start here with, if you think of this as my A and this is my B, I will go backwards. 0 plus 0 is 0. That's why these corners do not have to match. And you can pause and check them all out. 2 plus 3 is 0. 3 plus 2 is 0. So that is why our answer is yes, but the quicker way, again, is to check the main diagonal here for symmetry. So that makes it very easy. State the identity if it exists. Well, what is the identity? If I perform the operation, do I get the same result? In other words, I started with 0. Do I end up with 0? I started with 1. After the operation, do I end up with 1? So what I'm looking for is a column that's 0, 1, 2, 3, or 4. And it happens to be right next to it. That won't always be the case. So I have the exact same thing here and here. In other words, I started with 0, I performed the operation, and I ended up with 0. I started with 3, I performed the operation, and I ended up with 3. Well, what did I do? All I did, what was the operation or the element that I used was 0. So the identity is identity E is equal to 0. Again, why is that? Well, what did I do? I added 0 in mod 5 and I got the identity. Okay. D, verify that the inverse is equal to 2. Well, remember, the inverse states that if inverse is B, right, then A star B is equal to B star A is equal to the identity element, right? So let's say the inverse of 3 is equal to 2. Well, we have to look for the identity element 0, right? Well, here's 3, and when I perform the operation, when does it equal 0? Well, it equals 0 when I add mod 5, 2. So 3 plus 2 mod 5 is equal to 0. Okay, so there's my identity element, right? So that's the first part. C plus 5, or plus mod 5, 2 is equal to the identity element 0. And what about 2 and 3? Well, 2, right? 2, 3, ooh, it's 0. So 2 plus 3 is equal to 0 mod 5. So that implies that the inverse of 3 is equal to 2. Well, what about all the other elements? State the inverse for each of the other elements. Okay, well, let's start with 0, right? So 0 plus 0 is equal to the identity element right here, right? Maybe I should go in pink. That would be easier. And if I go the other way, starting with this 0, I get the same thing. And 0 plus mod 5, 0 is equal to 0. So that implies that the inverse of 0 is equal to 0. What about 1? Okay. Well, where's my 0? Here it is. What did I do to get it? I added 4. So 1 plus, in modulus 5, 4 is equal to 0. And what about 4 plus 1? 4 plus 1, that's 0. Giddy up. So 0 plus mod 5, 1 is equal to 0. So that implies that the inverse of 1 is equal to 4. And I think you get the picture here. So 2, negative 1. So let's look here. Where's the 0? What did I do to get 0? I added 3. So 2 plus 3 mod 5 is equal to 0. And 3, which we've already proved, 3 plus 2 mod 5 is equal to 0. So that implies the inverse of 2 is equal to 3. We already did 3 for D, so all we have left is 4, but that's just going to work out the same way, isn't it? So we'll go ahead and do it. 4 plus 1 mod 5 is equal to 0. 4 right here, 4 and 1. And 1 plus mod 5, 4 is equal to 0. So that implies that the inverse of 4 is equal to 1. So there we have it. Every time we added, every time we use the commutative property to add or to perform the operation, we got the identity element, and that is why we were able to find all these inverses. All right, hope you enjoyed it. Why wouldn't you? It's mathematics, so let's listen to some more days going by. And with that, I am going to say that I am O.